Hello everyone, welcome to a demo of my Tinycardia project. Tinycardia is a lightweight real-time cardiac event monitoring system built to address two major limitations in existing cardiac detection tools: affordability and responsiveness. Most consumer options like the Apple Watch need the user to sit still and initiate a reading manually, which limits their usefulness in emergencies. This is crucial because most of the time when you're going through a cardiac emergency such as atrial fibrillation, you do not actually know that is happening. So making the user sit still and make an on-demand request for an ECG classification is in some ways redundant. On the other hand, clinical tools like Holter monitors are continuous, but are also expensive and cumbersome. Tinycardia was designed to bridge this gap by enabling real-time arrhythmia detection on a low-power embedded system with no user interaction. The prototype uses an STM32 Nucleo development board paired with the ECG front end here, which is the MAX 3003. This is a single lead ECG sensor. It's a lot better than other options like the AD8232, I believe is the name. And the reason for that is because this is a clinical grade sensor, not a hobbyist sensor. And that results in a lower noise profile overall. You can also have more customizability with this chip instead of the hobbyist chip. You can change the resolution of the reading. So currently this is reading 256 samples per second or 256 hertz. And those samples are fed into the STM32, and the pre-processing and live inference is done here. And then we are also using this microcontroller to send the data to the laptop, which then displays on the Python GUI. And on the GUI here, we display both the real-time ECG waveform as well as a fast Fourier transform of the waveform. And this is useful to visualize noise. So right now you can see there's a slight peak at 60 hertz. This is just due to electromagnetic interference. And we also display the classification. So it will either classify between sinus rhythm or atrial fibrillation. And there are a lot more rhythms than these two, but because of the limitation of the single lead, we are using a modified lead 2 configuration. And due to that, you can only classify sinus rhythm or atrial fibrillation reliably. And that's what the model is trained on to do, and it gets pretty good confidence. The model itself is using a combination of one-dimensional convolutional neural network paired with a branch for R-to-R interval features. And we extract certain features so that from the R-to-R interval so that we can gain a knowledge of the temporal patterns of the waveform, and we use the convolutional neural network to understand the waveform in a morphological way. Now, one or the other gives you about an accuracy of maybe 70 to 75%, but on our validation set here with the two-branch model, we're able to get up to 95% accuracy. So overall, it's pretty accurate. It seems to work pretty well. There are future improvements that can be made for this product. So obviously the first one is making it portable. So adding stuff like a battery, a standalone display, and an enclosure would make this portable. The second improvement would be making this device wearable. So obviously in its current state, it's not wearable at all. But putting it in an enclosure, battery, and display, or even communication over Bluetooth to an app would be pretty nice to transform this into a fully functioning product, and then on top of that, getting an FDA clearance. Those are the top improvements that can be made to this project right now. But as a prototype, definitely seems to work pretty well. And yeah, that is my demo for Tinycardia.